Hello students, today in this video we will learn the average of order of d of n under the topic of average of arithmetical function. Before going to a theorem, let us recap some of the results. That is, if x greater than or equal to 1, then summation of 1 by n where n less than or equal to x is equal to log x plus c, where c is Euler constant, plus big O of 1 by x, and second result is summation of 1 by n power of s, where s is positive integer and but not equal to 1. So summation of 1 by n power of s is equal to x power of 1 minus s by 1 minus s plus zeta of s plus big O of x power of minus s. And third result is summation of 1 by n power of s, where s is strictly greater than 1, and whose result is equal to big O of x power of 1 minus s. And fourth result is summation of n power of alpha, where alpha is greater than or equal to 0. Therefore, the sum of n power of alpha, where n is less than or equal to x, is equal to x power of alpha plus 1 by alpha plus 1 plus big O of x power of alpha. The sum in the equation 1 count the number of lattice points which lie on the hyperbola QD is equal to n, corresponding to the values n is equal to 1, 2, 3, up to integral part of x. So in this right side we see the diagram. So the line shows the hyperbola, a classic hyperbola this is, and the points which are on this curve are the lattice points that satisfies the equation QD is equal to n. So if we join all these, we get hyperbola. For each fixed d less than or equal to x, we may count first those lattice points in the horizontal line segment, that is 1 less than or equal to q less than or equal to x by d, and then sum over all d less than or equal to x. Therefore, summation of d of n is less than or equal to x, double summation of 1 where d less than or equal to x and q less than or equal to x by d is equal to summation of integral part of x by d plus big O of 1 where d less than or equal to x. Here we use the result summation of n power of alpha, x power of alpha plus 1 by alpha plus 1 plus big O of x power of alpha. For alpha is equal to 0, the sum of n power of 0 as per this formula is equal to x plus big O of 1. Okay, see, summation of n power of 0 is equal to x power of 0 plus 1 by 0 plus 1 plus big O of x plus x power of 0 as per this formula summation of n power of alpha. This is the formula we use here when alpha is equal to 0. So when alpha is equal to 0, what is the summation of 1 is called x plus big O of 1. Now we continue. Therefore, summation of d of n when less than or equal to x of summation of 1 by d less than or equal to x plus summation of big O of 1 d less than or equal to x, and this is equal to x of summation of 1 by d less than or equal to x plus big O of summation of 1. Why we written like this? Because we know that summation of big O of 1 is equal to, when d less than or equal to x, big O of summation of 1. That means summation of big O of 1 is equal to big O of summation of 1. That means that is equal to big O of 1 plus dash dash plus 1 up to x times. Therefore, big O of x into 1, that is big O of x. Hence, summation of d of n, where n less than or equal to x, is equal to x into summation of 1 by d plus big O of x, where d less than or equal to x. Here we use concept summation of 1 by n less than or equal to x, log x plus c plus big O of 1 by x. So in the first slide, we taken some important result as a recap. So one of those results we have this one, summation of 1 by n, where n is less than or equal to x, log x is equal to log x plus c plus big O of x. We know that c is a Euler constant. Therefore, summation of d of n is equal to x times of log x plus c plus big O of 1 by x plus big O of x, and that implies summation of d of n is less than or equal to x is equal to x log x plus cx. We are multiplying x, the terms in the bracket. Therefore, we get x log x plus cx plus x into big O of 1 by x plus big O of x. Therefore, summation of d of n is equal to x log x plus cx plus big O of x by x plus big O of x. Among these values x power of 0, which is equal to 1. So what is the dominated term is obviously x. Therefore, summation of d of n is equal to x log x plus big O of x. Hence the theorem is proved. Now we take the corollary. The average order of d of n is log n. We know by a theorem recently, just now we completed, that is summation of d of n is equal to x log x plus big O of x. The average order of d of n is f of n, that is equal to 1 by n summation d of k, where k is less than or equal to n. So this is the average order of d of n is f of n. So now we calculate what f of n is what. So f of n is equal to 1 by n. Already we learned that summation of d of k as per the result above, n log n plus big O of n. Hence the next result is 1 by n is multiply the terms inside the bracket. Therefore we get log n plus 1 by n big O of n. And the next step is we multiplied the entire equation f of n is equal to log n plus 1 by n big O of n with log n. Therefore we get f of n by log n is equal to 1 plus big O of n by n log n. Taking the limit of the ratio when n tends to infinity, therefore the limit of f of n by log n is equal to 1 plus 0. Hence we understand that f of n is almost is equal to log n. That is, since why? Because limit of f of x by g of x is equal to 1, if it is possible, then we say that f of x is asymptotic to g of x as x tends to infinity. That's why we write here f of n is asymptotically equal to log n, or simply f of n is asymptotic to log n. Therefore, the average order of d of n is log n.